What's up, everyone? Before we deep dive into distributed system, let me tell you about one of the most expensive bugs in history, Night Capital. A major trading firm deployed new software that had a dormant piece of code. The code that hadn't been used in 8 years. When activated, it started buying stocks at market price and selling at ask price, losing all money every single trade. In just 45 minutes, they burned through $460 million and nearly went bankrupt. This wasn't a hardware failure or cyber attack. It was just a failure in three fundamental principles, which we are going to cover today: reliability, scalability, and maintainability. Now, if you are preparing for FAANG interviews, these concepts are absolutely critical. System design questions will test your understanding in these three pillars, and I'm going to break them down in a way that make you stand out from other candidates. Okay, so let's start with reliability. In distributed systems, reliability means system continues to work correctly even when things go wrong. And trust me, things will go wrong. There are three main categories of faults in this handle. First is hardware faults, then we have software faults and human faults. Hardware faults are hardware crashes, RAM becomes faulty, power goes out. And the solution, redundancy. Add redundancy to every component, use RAID for disk, have backup power supplies, run multiple instances across different machines. Second is software errors. These are systematic errors that are correlated across nodes. Think about a leap second bug that crashes all your servers simultaneously, and a runaway process that uses up the shared resources. These are harder to anticipate because they are often triggered by unusual circumstances. Third is human errors. Humans are unreliable. We make configuration mistakes, we deploy the wrong software, we accidentally delete the wrong database. The key is designing systems that minimize the opportunities for error and make it easy to recover when errors do happen. Now let's deep dive into the hardware failures. At Amazon scale, hardware does fail constantly. In fact, if you have 10,000 disks, you can expect at least 10 to fail every day. The solution is redundancy at every level. For storage, you use techniques like RAID, where data is distributed across multiple disks. Now, if one fails, the others can reconstruct the missing data. For compute, we run multiple instances of our application across different machines, different racks, even different data centers. Load balancer distribute the traffic and automatically route around failed instances. For networking, we have multiple network paths. If one switch fails, traffic automatically routes through the backup paths. The key insight for interview in this is don't just add redundancy. Add uncorrelated redundancy. Having two servers in the same rack doesn't help if the entire rack loses the power. Now, software errors are scarier than hardware failures because they are correlated. When a hardware component fails, it usually affects just one machine. But when there's a software bug, it can bring down entire fleet simultaneously. I have seen this happen. A memory leak in a logging library brought down hundreds of servers at once. A configuration change caused all instances to connect to a wrong database. These systematic failures are what keeping engineers up at night. The defense strategies are different too. You need comprehensive testing, but not just JUnit test cases. You need chaos engineering. Chaos engineering is deliberately breaking things in production to see how your system responds. Netflix pioneered this with Chaos Monkey tool. You also need gradual rollout. Deploy to small percentage for your fleet first. Monitor for issues, then gradually increase it. This is exactly what Night Capital failed to do. Now, for human errors, the key is good design. Make it easy to do the right thing and hard to do the wrong thing. Use infrastructure as code so changes are reviewed. Implement circuit breakers so failures don't cascade. And always have a quick rollback mechanism. Now, scalability is your system's ability to cope with increased load. But here's what people get wrong. It's not just about handling more load, it's about maintaining performance as the load increases. Load can be many things. For Twitter, it's tweets per second and timeline reads. For Netflix, it's video streaming bandwidth. For Uber, it's rides per minute in specific geographic area. Now, there are two ways to scale. One is vertical and another is horizontal. Vertical scaling means getting a bigger machine, more CPUs, more RAM. It's simple, but has its limit. You can't buy infinitely powerful machines because they get exponentially more expensive. Horizontal scaling means adding more machines. This is what cloud native applications do. Instead of one powerful server, you have many smaller servers working together. But horizontal scaling introduces complexity. Now you need to do load balancing, data partitioning, coordination between the machines. You need to handle the fact that some machines might be slower than others and might even fail entirely. The key insight for interview here is understanding the trade-offs. Vertical scaling is simpler but limited. Horizontal scaling is more complex but gives you unlimited growth potential. Let's talk about performance metrics because this trips up a lot of candidates. The two key metrics are latency and throughput. And they're not the same thing. Latency is response time, how long it takes to process a single request, whereas throughput is how many requests you can handle per second. You can have high throughput with terrible latency and great latency with low throughput. Think of it like a highway. Latency is how long it takes for one car to go from point A to point B. Now, throughput is how many cars can travel through the route per hour, like this. How many are there? You can increase the throughput by adding more lanes, but that doesn't necessarily reduce the time for individual cars. Now, for coping up with load, you have several strategies. The first one is caching. You can store frequently accessed data in memory. This dramatically reduces the latency of common requests. Load balancing, distribute requests across multiple servers. This increases the throughput. Asynchronous processing. Don't make the users wait for slow operations. Queue them up and then process them in background and then you send them the update. Then we can have database optimization. You can use read replicas, partitioning, indexing to handle more queries. Now here's a stat that should scare you. 80% of software cost happens after the initial release. That's maintenance, bug fixing, adding features, adapting to the new requirement. This is why maintainability is very crucial, especially in man scale or any software interview. Maintainability has three aspects. First is operability. It makes it easy for the operation team to keep the system running smoothly. This means good monitoring, clear logs, predictable behavior, and automation for routine tasks. Now, if you've worked on systems where deployment required 20 manual steps and took 4 hours, compare that to a system where you push a button and everything happens automatically. Which one do you think has fewer outages? Second is simplicity, but not the kind you might think. It's not about having fewer features, it's about managing the complexity. Good abstractions, high complexity behind clean interfaces. Microservices can increase operational complexity, but they reduce the conceptual complexity by separating concerns. The third is evolvability. This is the ability to adapt to the changing environment. This is where good architecture really pays off. Systems that are easy to modify and extend survive longer, cost less to maintain. Now, let me break down these three aspects of maintainability with concrete example. For operability, you've seen Definer dashboards. Your system should tell you what's it doing. Good metrics, structured logs, distributed tracing. When something goes wrong at 3 a.m., you want to know immediately what's broken and how to fix it, right? Automation is the key. Deployment, scaling, backups, and monitoring setup. Anything that can be automated should be automated. Human operators should focus on high level decisions and not the routine tasks. Now, for simplicity, the goal is to manage essential complexity while eliminating the accidental complexity. Essential complexity comes from the problems you are solving. Accidental complexity comes from poor design choices. Use proven patterns and technologies. The best systems are often the boring. They use well understood components in predictable ways. For evolvability, design for change. Use loose coupling between the components. Make it easy to add new features without modifying existing code. This is where good API design and clean architecture patterns really shine. So there you have it. The three pillars that could have saved the night capitals $460 million, and more importantly, the framework that'll help you ace your man interviews. Remember, reliability is about working correctly when things go wrong. Scalability is about maintaining performance as load increases. Maintainability is about long term cost and adaptability. So, when you're in that system design interview, don't just jump into drawing boxes and arrows. Start by asking about reliability parameters, scalability needs, maintenance constraints. This shows you think like a senior engineer. Now, if this helped you, smash that like button, subscribe for more system design content, drop a comment with the toughest interview questions you've ever faced. Until next time, keep building reliable, scalable, and maintainable systems.